Hey, welcome back to Vectors Part 2. Good to see you again. This presentation is about a little bit more of the geometry of vectors, and we're going to be constructing vectors of various lengths. And what we're going to try and do is find also the angle between vectors and the angle that the vectors might make with the positive direction of the x-axis. Over here, we've got a screen clipping from Pearson's textbook. This goes a little bit beyond the scope of the course, more into a physics problem, but you might have a look at that in the book. We won't be dealing with that in this course. The course doesn't go quite into that degree of complexity. Fairly basic treatment. Okay, are you ready? Have you built up some skills? We're going to be taking those to another level in this presentation. So come on down and let's look at some questions I've already mentioned. And here's the first one. Can you find the angle a vector makes with the positive direction of the x-axis? What's that? Hey, here's the x-axis. The positive direction is going to the right there. So we want the angle like that. That position vector, you can see the angle easily. Whoa, u and v are equal, aren't they? Certainly look to be. I think if we work that out, they are the same vector. And that angle would be the same. So we're going to find that angle even if, go back and I'll rub that out, it doesn't intersect the axis. We can still find it. Let's see if we can do the maths on that. Okay, well, what is the maths on that? Well, if we take the position vector, and that's the angle we want, what do you notice? We did this with straight lines before in coordinate geometry. Can we do it in vector geometry? Let's do a construction down here. I think we can, because the tan of theta would be, if you like, just the old one, opposite over adjacent. And what is that? That's 5 take naught over 2 take naught. It's the old coordinate geometry, y step over x step. So if vector PQ has components there, 2, 5, the tan of theta, the angle it makes with the positive direction of the x-axis, is going to be the y over the x component. Paralleling what we did with delta y and delta x for the slope of a straight line in coordinate geometry. Only this is just a little bit neater. Are you starting to see now that the components here of this vector are in sort of reverse order of the slope, aren't they? We put x on the top and y on the bottom. And when you plot that, that is y step over x step, the other way up. Do you get it? And we could do it for this vector here. Let's do it for this vector here without any construction. Let's say we happened upon this vector, v, just walking down the street or something. And it's 3, 1, 5, 6. We would say vector rs is equal to, what's the x step? 5 take 3, which is 2. And 6 take 1, which is 5. And so the tan of theta is 5 over 2. We said they were equal, so it checks out. But I'm just saying here in this one that you don't actually have to have a diagram. You could just have these points here and here. And then you could still get the vector form and then use those components. Okay, do you get it? Okay, we'll be doing some of those later on. And we'll be doing them in the next quadrant as well. So over here, if we had a vector out here, then we'd be looking at that angle. Okay, so we do the same operations, but we would be getting the angle and between the vector and the positive direction of the x-axis. Just remember the association, remember the result in coordinate geometry land for y equals mx plus c, then m, the slope, is the tan of the angle that the line makes for the positive direction of the x-axis. It's this angle here, not the other side. Okay, a bit of revision there. Okay, we're building up, aren't we? We're trying to actually say geometry in vector land is probably neater. Can we do everything we want? We can find lengths, find direction using component form. Now we can find an angle. Here's the next question. Can you find a vector in the direction of AB but with a size of 3 units? Well, that's interesting. I reckon we've got to say, what's the size of AB to start with? Is that the first question? I don't know. Vector AB, let's look at its components. You could do this sort of stuff, but we want to go away from that a bit because we're not always going to have a diagram or need a diagram in our vector work. So here we could say A is 2, 2, and B is 5, 6. So the vector AB, 5 take 2 in X-land, and 6 take 2 in the Y. So vector AB is 3, 4. Okay, so the length of AB, doing it down here now, the length of AB, remember this from before, square root of 3 squared plus 4 squared. I've done nice numbers here, root of 25, Pythagorean triple A. Okay, so here, length of AB is 5. Now we only want a little dude, smaller than that. We wanted a vector of 3 units in length. Why don't we create what we call a unit vector and then multiply it by 3? What's he talking about? Let's go over here. A unit vector, 1 unit long, in the direction, so we're going to capture the direction of AB. In the direction of AB, that's what we want, a unit vector. So, let's have a look at it. How would we make AB 1 unit long instead of 5? Oh, multiplied by a scalar, isn't it? What if we considered the vector 1 over 5 lots of AB? 1 over 5 times AB. What would its length be? Well, would have the length of 1 over 5 times AB would equal 1, wouldn't it? Because we're dividing each component by 5, and you will have a vector fifth the length. So the unit vector we're looking for in the direction of AB will be equal to a fifth of 3, 4, which is 3 fifths, 4 fifths. Let's check it out. Check out the length of that now. Let's make sure it works. The length, which is that symbol, size or absolute value of a number, and we're going to use the same symbol in vector land, is the square root of 3 fifths squared plus 4. It must work because we've multiplied by a fifth, but let's just check it. Make sure you're happy. 9 25ths plus 16 25ths, root of 25 25ths, adding up the 2 lots of 25. So here's a root of 1, which is 1 because it's a positive length here. Length is greater than 0, if you like. Just explaining why we have taken the positive root. Okay, so here we don't really need that there because we've said this is the positive root, the principal root up the top here. Anyway, so it's 1. It works. So how do we create a vector of size 3 units, our original problem? Therefore, the required vector, being 3 units long, would be equal to 3 lots of this. 3 times the unit vector in the direction of AB. Or if you like, 9 fifths and 12 fifths. That would be our 3 unit vector. And you can check its length if you like. Okay, the required vector there. Alright, so that's not a bad idea. What have we just done now? We have captured the direction of AB by making a unit vector. A vector which is just 1 unit long. And then we can multiply that up to any length we like. Not a bad little trick, is it? To find a vector in the direction of another vector with a size of anything. Let's come down and summarise those 2 little pieces that we've just done, and then we'll practice those. Okay, here they are here. First of all, the tan of the angle that the vector makes with the positive direction of the x-axis is the y component over the x component. The unit vector, if you want to create one in the direction of a certain vector, is that vector. See, I've got in bold here. So that is a vector, and this is 1 over its length, using the modulus or absolute value notion again to imply size, this time in vector land, the size of vector u. Can't do it in bold, just writing on the screen here. So once we've got that, this actually captures the direction of u, doesn't it, without any funny magnitudes, like 3, 4, 2.8 or whatever. It creates a unit vector. Then if we want a required length vector, you multiply it by, there's the required length, a scalar lot of that. And that multiplies it up to any length you want, still capturing the direction of that vector. So that could be handy. If you want to say on a boat, the wind has got a certain force, so many newtons, what would happen if that dropped or increased to a certain value? And you can create that certain strength or value or magnitude of your vector using this process, a unit vector approach. Okay, are you ready? Let's have a look at what we can do with it. Here's a screen clipping from Pearson's now. Find the direction angle to the nearest degree of each vector. That we taught you this direction angle is the angle that the vector makes with the positive direction of the x-axis. And find a vector of magnitude 7 that is parallel to each. Alright, so we've got to do the processes to each of these. Notice I've gone to the basic vector form, as it's mentioned in the syllabus, the IJ form. You might like to change that to 2, 2 and neg 3, 3. Please yourself. This column vector approach is mentioned explicitly in the syllabus, and so is the IJ approach or format. Okay, let's have a look at this first one and then do the others, and just come in and join in here. Direction angle for u is theta, as shown in figure 8.15 down here. So that's the same for u. A vector of magnitude 7, oh hang on, we better do it. So tan theta is 2 over 2. Why is that? Let's go back up screen here. Here it is, components. That's a y component over the x component, so the angle is 45. Are you happy with that? Okay, so a vector of magnitude 7, what are we going to do? Well, there's our vector in I and j form. What's its length? There it is, so we divide by its length. So this part is giving us a unit vector. The vector divided by the scalar, which is its length, right? And because of the scalar, it is just a number, and then we multiplied it up to 7 units long. So if we do that, we get this answer. It's pretty unwieldy, but there it is, and we can go to the end of the red vector, and this will be 7 units long. Okay, now that's what we're doing. Let's do it again for the next one. Next one is neg 3, 3, or neg 3i plus 3j. So this time, it's over here, neg 3, 3, right, neg 3 in the x and 3 in the y, and we've taken it from the origin. We could put it anywhere, remember, the non-unique specification of the vector neg 3, 3. Please note that this notation from Pearson's is not preferred by the syllabus. They like the column vector, this one here. Anyway, if you plot that, we find this is the angle over here with the positive direction of the x-axis. Okay, that's important. It is not going to be this angle in here. Okay, so let's have a look. Tan of theta up the top here, neg 3 over 3 is neg 1. Therefore, theta is what? Well, the tangent is neg 1. So that's this angle in the second quadrant. So it's 180 minus the working angle. Working angle whose tangent is 1 is 45. It's in the second quadrant, clearly here. So it's 135. Now this is a bit naughty here. This theta is in the wrong place, isn't it? Okay, the theta is, look up here, the theta is 135. Well, that's naughty. That should be over there with the positive direction of the x-axis. So just watch that there. that is an angle in there, but the angle we're getting here is with the positive direction of the x-axis. This theta up the top, come up here, this theta is 135. It isn't that one there. That's the working angle theta. Okay, let's now also do a magnitude of 7. So what are we going to do? Get vector v, divide by its length. There it is. There it is. In IJ land, and then multiply it by 7, same as before. So we get some funny numbers here because these vectors are all of different length, and when you reduce them down to a unit vector, that over that, those two divided, then you might get some funny fractions. And you must be prepared to work in IJ form or in column vector form. So what would this be? It'd be 7 on root 2, because that component's neg 1, neg 7 on root 2, and 7 on root 2. Okay, in the other column vector form, component form like that. Let's have a look at the last one now. The vector here. Now this is correct, that's the angle it makes for the positive direction, and if you plot this last vector, 3, here it is here, so 3i take 4j is our vector w, or we could write it as 3 neg 4, and there it is down there, we go 3 in the x, there it is, and then 4 in the y, so this is the vector 3 neg 4 preferred column vector notation, and of course the angle it makes for the positive direction of the x-axis is that theta there. That's correct this time. So tan theta is neg 4 over 3. That checks, and if you look that up, it's working angle of 53 degrees, working in degrees here for this sort of work in geometry. And it would be neg 53 because you're coming down this way quite clearly. Okay, what about a vector of magnitude 7? Same thing again. This shouldn't be u here, it should be w. W divided by its length to get a unit vector, and then times by 7. Same stuff again. This time it works out more nicely. The length of that vector is 5 units, like the example I used before. So it's 7/5 of that. Or you could put it as 21 over 5 and neg 28 over 5 if you wanted to multiply it through by 7/5. Okay, get the idea? Quite a powerful tool if we're going to work with vectors later on. We don't do much with vectors in this course. We learn the basics only. Here are Pearson's exercises. So what I want you to do, direction angle, we can interpret that with the angle made with the positive, remember, direction of the x-axis. That's important. Okay, I'd like you to do all those. Question 1 and 2, I'll roll through these and then show you the answers. Okay. Alright, away we go. 3, 4 and 5. I've cut out the rest for the moment, well, for this course in actual fact. 6 onwards are applications that are beyond the scope of this course. We will look at some applications later on. Okay, so writing each of these vectors in component form, you've got to go backwards. You've got the angle and the length of the vector, so you might be able to work out the initial components, and then you've got the length as well. Okay, so have a look at that, see if we can work backwards there. Find the unit vector in the same direction here, well that's alright, and find a vector. Okay, so we'll look at those. They should all be able to be done by thinking about the examples above. Okay, we'll pause it and have a go. Let's go and look at the answers now. Here we go. So question 1, A, B and C. Bring D up now. Just a note here, arc tan is equivalent to tan neg 1 of theta. Just noticing that there, that's setting out. Let's go down to E. There E and the start of 2. A sketch helps in this, of course. let's bring all the 2 up there. So we can, A, B, C, D and E. Okay, then we go to F and question 3. And question 4 and 5. Okay, so have a close look there, particularly at question 3. That was a sort of a hard one. Might have to discuss that with your teacher, that one. All right, let's go on and look at our next question in this developing geometry ideas with vectors. Okay, can you find the angle between 2 vectors? That's an interesting question. So this time we're looking at the angle there between A and B. Now, I want you as a budding young mathematician to join in here and say, what would I do? To find an angle like that from the geometry you know so far, what would you need? You've got sine rule, you've got Pythagoras, cosine rule, trigonometry, but what do they all require? They all require a closed figure. Actually, they all require a triangle. So what would you do? Let's make a triangle here. Maybe make the vector go that way. That should be right up there. Hang on, I'll just complete that. I hope I will. Let's complete this. A little glitch there, but we're back here and I've completed that side here. But what would it be here? What would it be as a vector? Now we should be able to work that out as a vector by using the sum of vectors around a closed figure. So if we called it vector u, what do we notice? Starting from here, let's go to there. Vector A plus vector u, no, take vector u, isn't it? If I put the arrow that way, there we go again. So just pause that now. So doing that again there, we've got A take u, so that's good. So we've gone to there, then neg u, going the opposite to that, and then we come back down here. Neg b would equal the 0 vector. Let's move u on the other side. A take b would equal u. Alright, okay. So this side, coming back up the top here, u is actually A take b. Are we getting anywhere? Well, we've got the triangle with vectors around it. How do you find an angle in a triangle like that? What are the 2 options, do you think? 2 options in this triangle. No right angle, there's a clue. What are the 2 ways of working out that angle? Did you think first of maybe the sine rule? Yeah, that could be a bit harder. Or the cosine rule. You could play with each of these. What I want to show you now, and this is a cross-link particularly mentioned in the syllabus, the use of the cosine rule to develop what we're going to do now, that finding the angle between these 2 vectors. So, how would we do it? Well, there's the angle there. The cosine rule says, what? Let's start, we need plenty of room for this, so let's start right up the top here. Cosine rule says the length of any side squared is the sum of the squares of the other 2 sides. Are you seeing this on the diagram as I write it? Minus twice the product of those 2 sides. Oh, I should put A first maybe, don't worry. By the cos of theta. That's the cosine rule. We could use that maybe to find cos theta here, the angle between 2 vectors, because it makes sense as we move up in vector land to develop some geometry with it. So how are we going to do that? How are we going to find these lengths here? Okay, all of these. Let's look at writing A and B in component form. What about that? So come over here. Let A be the vector A1, A2, and B be the vector, this is a proof now, B1, B2, so you can't actually use specific numbers, you've got to use deductive reasoning, not inductive reasoning, and so A take B would be the vector A1 take B1 and A2 take B2. Okay, let's now go back over here and write down the length of A take B all squared. So what will that be? Well, we'll write this in first. This will be the length of A1 take B1, A2 take B2, length squared. This is the length of A1, A2 squared. A lot of work here. The length of B1, B2, oops, left out the square up there, squared. And we'll just leave this at the end here for the minute. Okay, you'll see why later. Okay, can we work out these lengths? Okay, that implies, we might have to come over here just a little bit. This implies the length of that is the square root of the sum of the two components squared, isn't it? Oh, looks messy, but I've done it before and it comes out nicely. That's the length, and then we've got to square it, so that'll knock out the root sign in a minute. Then the next one is the square root of A1 squared plus A2 squared. It's the length of that vector, and then we're squaring it for the cosine rule. Length of B1 squared plus B2 squared, and then we've still got this dude on the end. I'm leaving it that way for a reason that you'll see in a minute. Okay, so what does this mean? Well, squaring the root means we've only got this there for underneath here. So let's expand that. This would be A1 squared take 2A1 B1 plus B1 squared. And the same here, A2 squared take 2 A2 B2 plus B2 squared. And that equals, now same thing here, the square, if you like, cancels out the root sign. The square of a square root is just the quantity, so let's write those down underneath here. And the same for this, square of a square root, B1 squared plus B2 squared, take 2 length, and cos theta. Oh, what do you notice? Let's take A1 squared from both sides, A2 squared from both sides, hey, this is magic, B1 squared, B2 squared from both sides. What do we get? Let's have a look. Neg 2 A1 B1 take 2 A2 B2 equals neg 2 length of A, length of B, cos of theta. Let's divide everything by neg 2. Okay, so this becomes A1 B1 plus, the neg 2 went out, A2 B2 equals length of A, length of B, cos theta. I think we're almost there. Let's divide by these two. So A1 B1 plus A2 B2 divided by their two lengths, without putting all the squares in, is the cos of theta. Now that's interesting. What does that say to you? Well, here it is up here, come up here. If you know A and B, the two vectors in component form, all you've got to do is get this funny product. What is this? X coordinate of the first one by the x coordinate of the second plus y coordinate of the first by the y coordinate of the second. That's an interesting product, isn't it? It's actually a sum of two products. If you do that with the vectors and divide by their lengths, which you could do, length of A is root of A1 squared plus A2 squared and B. So, hey, we've got a formula. We've got a formula. Are you excited? Because we can find the cos of the angle between two vectors if we know their components. And we do this funny product up here. Look at where it came from. Up here, the expansion up there. And divide by the lengths, and we would have the cos of the angle between them. We've just completed our geometry, I think. So now we'll be able to show where the lines are perpendicular, find what angle are between them. I think this is exciting. All right, let's formalise this, because we give a special name to this product that's arisen. I would like you to think of this product as arising from our desire to find the angle between two vectors. Let's have a look now. And there we do have a name for it. It's called let's just bring all this up, the scalar product. So it's not just completely a product, is it? It's actually the product of the x components of the two vectors, and it's a sum with the product of the y's. But we call it a scalar product. Now, why is it a scalar product? Well, it's not a vector. It's the sum of all those numbers. So it's just a number. So it's a scalar product. Now, there is another product that we use with vectors, a way of combining them in a product form, called the vector product. Now, that's not in this course, so we have to be careful when we mention doing this, so we don't just say the product of the vectors. We must say the scalar product, because although we don't do the vector product in this course, there is another product. It's a product designed to find a vector perpendicular to two other vectors. Okay, so that's the idea. But that's not in this course, as I said. So if you know two vectors in component form, what have we just shown? This product is special because the cos of the angle between the two vectors is this product over their two lengths. So we're going to give a symbol and a name. So this is the u dot v, so it's sometimes called the scalar product or the dot product, because we use a dot, not a cross, to represent it. The cross between two vectors is used for the vector product, not in this course, as I mentioned. And it's just a name for this rather interesting product that we've just derived back there. So given two vectors, you can get this product. And then if you divide by the lengths here, ooh, wow, you found the angle between two vectors, or the cos of the angle between two vectors. Okay, and then you've got to say, well, the angle is cos neg 1 of u dot v over length u, length of v, and you could call this arc cos, as we saw in the answers above, the inverse function. But you don't have to do that here. Okay, in this course. So what's another rearrangement? You could say, when I find the dot product, I'm actually finding length of u by length of b by cos theta. Just so that's a rearrangement of this, isn't it? Okay, so it's delving in to the geometry of the vectors there on the plane, working out the angle between them, lengths and so on, and looking at ways of manipulating it. So this is a very, very powerful tool for understanding the geometry of vectors and working with them. All right, so let's practice that, shall we? There's the page, so let's check that out and see what we can do with it. So going back to Pearson's with a example now. So we've got two vectors, v and w, and you must be flexible. The column notation, we could have that, and 2 neg 4, either form. So what are we going to do? To find the angle between those two vectors, we'll get the dot product divided by the lengths. And that's this funny product. Neg 3 by 2, but you know where it came from now. And then 3 by neg 4. And add them up. A1, B1 plus A2, B2 if you like. Divide by their lengths, same as before. Square root of the sum of the squares of the components. Then we get this. And theta would be, because it's a negative cosine, what they're saying is when we do this and we do the vector v and the vector w coming from the same point and it's negative, that means that angle will be obtuse. It gets this dot product gets the angle from the common point if you take the vector going outwards. Okay, you can't actually have one going in and one going out. So if you want the angle between two vectors, you must get their form like this, going outwards from the point. You'll get that angle. That's vector A and that's vector B. But if you have one going the other way, if vector B is going in, you'll actually find this obtuse angle here. So we've got to be careful. Okay, we want them, if this is going to be the angle, the acute angle between them there, you need to know that they're both emanating out from that point. Okay, and then you would be finding that angle in there. Otherwise it's the obtuse angle on the other side. So this one looks like this. Oh, well, you could actually plot it, but it's got an obtuse angle in there because we've got vectors going out from them in that order, probably. We'd have to look at that to see what the geometry of that was. Okay, so we've got an obtuse angle in there. Now, we're not actually sure they're emanating from the 2 points here, so when they say angle, they usually ask for the acute angle so that we know what the geometry is. All right, let's come down and look at an important result now. Obviously, if we're using vectors in geometry, what we need to do is to say, have we got right angle triangles? Because then we can use trigonometry in conjunction with it, or Pythagoras. So, let's do it. If theta is 90, let's look at what the dot product becomes. Length of V by length of W cos theta. That's the other form, remember. You could use this though. Cos theta is V dot W over length of V, length of W. And if these are perpendicular, the cos of 90 is 0. Okay. Now this would do it over here in the same way, if you like, either form. Now for that to be 0, the dot product must be 0. So that's what they're saying here. Cos of 90 is 0. Therefore, the dot product will be 0 when the two vectors are at 90. This is important. We now have a test for perpendicularity, if you like, either using this form or the multiplied out form there. So there is a rule. If vectors are perpendicular, their dot product is going to be 0. Okay, if vectors are parallel, we've already seen this before, then one is some scalar multiple of the other. That was way back in the first presentation. If you just multiply a vector by an ordinary number or a scalar, you will keep its direction but be longer. So V, or shorter, k could be a fraction, or it could be in the opposite direction, and k could be a negative. If you just multiply some vector by an ordinary number, all it does is change its length. Or it could go in the opposite way, but it will be parallel. So there are two very, very important tools, because the course does involve talking about the geometry of vectors. Are they perpendicular? Are they parallel? So you must note that one down now. That's important. All right, let's have a look at some examples now. And we want to do most of these here and see what you come up with. You don't actually have to know the properties of the scalar product. We're going to look at them here. You must be able to do these expressions though, work out the expressions, but what you'll find is this one and this one are equal. You don't actually have to remember that u dot v, that dot product is distributive over addition there. They should be the same. You don't need to know those rules, just play with those and write a paragraph about what you've just found. I've given you one of the results already. Okay, finding the interior angles of triangle ABC. Have to be careful about the direction here. Triangle ABC. So if you want angle A, it's got to be using AB going that way out and AC going that way out from A to get that inside angle. So be careful with your direction of your vectors there. This is also in the course, working with simple figures, simple geometric figures here. Okay, so have a look at those. I'll give you the rest now, and then I'll give you the answers. So that's question 5, 6, 7, 8. They've got them all there now. Okay. So we'll take a bit of time to work with these now. Okay, so work carefully and think through it so that we can move on to the next exciting instalment. Let's have a look down below at the answers now. Okay, here we go. Question 1. Let's just bring that up a bit. Question 1, the 4 parts there. Go to question 2, 2 and 3. Question 4, A and part of B there. Let's just finish that off. B and C. From 5, 6 and 7. Eight, 9 and 10. 11 and 12. Just remember, the general rule here is if you are given IJ notation, usually stay in that notation. Okay, if you're given ordinary component notation, usually stay in that notation. Let's go down and have a look at some practice questions summarising from Pearson's their first section on vectors. Okay. Have a look at those. 3 and 4. I think about 9 of these. I'll just go up and get all of 5 and 6. Still only part of 6. Bit of a challenging problem. We're going to do that later on actually. Let's go up to 7. And the rest 8 and 9 there. So have a look. Some interesting questions there. Some stuff we haven't discussed yet. We might wait for the next presentation for that, doing it in slightly different format to Pearson's. Okay, let's look at some answers now. One to 3 there. Question 4A and B. Part C. Question 5 and start of 6. Let's look at question 6. Rest of question 6 there. Question 7. And the last bit of 7. Let's go up maybe just a little bit there. Okay, come down and let's look at 8. And 9. All right, fairly challenging questions there. Don't worry too much about the motion ones because we will be picking up on those in the next series of presentations in Vectors Part 2. I hope you're getting excited about your skill level. Keep working hard at it, go back over it and see what you think. Cheers for now.